Let's start class. Today we're going to talk about Gauss curvature and the mean curvature. Well, the second fundamental form, it indeed tells you how curved are the surface in a three-dimensional space in any given direction, roughly speaking. Okay, so here's a so give a surface, right, and give any direction v in the tangent plane. This is called tangent plane, right? So second fundamental form in that direction. Of course, this can be very arbitrary large. Okay, this is if you extend the length of v, then this will be changed, right? So this is actually the fundamental. You can use two variables, use one variable. So this is if you use two variables, this is just the value of VV, right? Second fundamental form can be a bilinear form or just quadratic form. Either way, they determine each other from linear algebra point of view. Okay, so this is if you extend it, then this lambda squared. Okay, so the geometric meaning of this second fundamental form, this is actually tells you if you have to normalize it. When I normalize it, the length of V is a first fundamental form. This ratio is the curvature we call the normal curvature. Okay, usually, we give a name here as normal curvature. In the direction of the surface S at the point P in the direction of V. Okay? And it's independent of the length of V you choose. Okay? So in that direction, how the surface curved in the space. If you assume a V is a unit vector, then the denominator is going to be 1. Okay, then just the second fundamental form, the value of second fundamental form in the direction of V. Okay. Now, the second fundamental form can be described in a different way. Right? So here a surface, right? For surface, you have the so-called Gauss map. And that's a Gauss map, right? Point P, and this is and the defined using the normal vector, right? This is the normal vector. So which is in S2, the image, right? So this is S2, three-dimensional space. This is S, the surface. Okay. So the second fundamental form is nothing but this can be using two vectors, V, W. This is nothing but the differential, okay, in the vector V, the dot product with W. Okay, this actually one can also show that this is a V dot dpg W. Okay. This is the second one relationship between the Gauss map and the second one form. Okay. This differential of the Gauss map is also studied by Weingarten. So that's why it's also called Weingarten map. So the differential of the Gauss map and actually can be viewed as a map from tangent plane to tangent plane. So so WP is going to be negative dpg. This is called, either you can call it negative differential of Gauss map, or it's called Weingarten map. Right? So this is a linear map. Right? Based on the above identity, WP standard vector, the inner product has this very important property. Okay. Now, those are the very abstract notations here. Linear map is independent of any local surface patch. Okay. Now, in order to compute it, you have to introduce a surface. Okay. In order to compute it, then you have to use a surface patch to do computation. Okay. All right. The surface patch, okay, so to compute it. So, yeah, if you want to compute it, then all this quantity, okay, is defined. Yeah, this is a surface patch. U and the V. Some open domain here, right? Okay. Then using surface patch, you can, the Gauss map, right? And define it in the following way. It's actually send the differential. So actually it's going to be, and the normal vector will be also a function for UV, right? So the normal vector, U and the V is going to define the normal vector evaluate at this point. So actually the normal vector field is a function for UV, okay? So you can differentiate, okay, for the vector. Okay, so this is a Gauss map. Okay, it's just the normal vector field right now is a vector vector function, so you can find partial derivatives. Okay. So yes. Okay. So the Vingat map, right? And that is also going to be negative lambda nu minus mu. All right. Those are the formula in the local coordinates. Okay, the second fundamental form. It depends, right? And that is going to be so if it's v, right, and uv, then you can use the two variables, right? So I just use a v. Okay, so that's going to be lambda square L 2 m lambda mu and n mu square. Okay, so this L and m, you can do the computation. This is u sigma u m and u sigma v. I think n is n v sigma v. Yeah, because this is the same as n v sigma u. I'm pretty sure. Okay. This should be negative, right? So it's negative. Let's double check. Yes. Yes. Okay, because so either of them, right? This is going to be n sigma uv, and who suppose it? Okay. This will be n sigma vv. This will be n sigma uv. So those are the local formulas. So in linear algebra, right? This Vingat map, which is negative Gauss differential of the Gauss map. Okay. This is a linear map, right? Okay, is a self-adjoint linear map. Okay, so for an arbitrary basis, right, in linear algebra, right? So you can talk about determinant of the map and the trace of the map. Okay, so you let E1, E2 be a basis for this plane, two-dimensional plane, right? You can find a matrix, okay? So how can I describe the matrix? So this will be A, B, C, D, for example. Different bases, you get different matrices, but they're all similar. Okay? If we change the bases, okay, then the relationship, yeah, if we change the bases, yeah, let's see. If this is another basis, right? And I'm going to say E prime, E2 prime. Then we have a matrix P here, right? Okay. Then I want to find the relationship, and this is the E prime, right? And this is A prime, C prime, B prime, D prime. Right? I want to find the relationship between those two matrices. So you just put it here. So WP, right? So then you act on this, right? And this part will be E prime, E2 prime, and A prime, C prime, B prime, D prime, and this is a P. Okay. But according to this identity, this is E1, E2, and the inverse, right? So this is a part is nothing but, because W has never been changed, only the basis is changed. So this is so A, B, C, D is going to be related to, right? So clearly the determinant AB, right, is the same as the determinant of, so it's really independent, that's a review of the linear algebra, really independent of the choice of the basis, right? And then the trace of the matrix, that's the sum of A plus D, okay, the number on the diagonal. And based on this identity, it's the same, okay? It's going to be A prime plus D prime, which is a trace of this matrix, okay? So because of that, we can define this to be the determinant of the linear map. And this can be the trace of the linear map. Okay, to define the trace of the linear map is very abstract. You have to choose a basis, then get the matrix, then you add all the elements of the diagonal. But you have to prove that it's independent choice of particular matrix. Okay. All right. Now, we also know that, okay, because by the self-adjoint, this, so this WP, okay, using this property, for any V and W is called self-adjoint, then you can, there is an orthonormal basis, okay, orthonormal with respect to the inner product, okay, so E1, E2, okay. So that means E1 dot E1, E2 was 1, orthonormal basis such that WP equals K1 E1, WP equals K2 E2. And in other words, the corresponding matrix is going to be E1, E2, is going to be K1, 0, and K2. Okay, so actually you find an orthogonal matrix such that the corresponding, find the basis such that the corresponding matrix is a diagonal matrix. So in this case, the determinant of this will be K1 times K2. Okay, the trace of WP is K1 plus K2. Okay, right? The trace, just add them together. So those are the quantity. Those are the quantity associated with the Lingard map. It's independent of choice. Well, yeah, those are the special quantity. Okay. So using that, then the second fundamental form is if you use this, okay, the second fundamental form, okay, this is going to be WP, right? V dot V. So it's going to be lambda squared K1 mu squared K2. So it's completely determined by K1, K2. So those two numbers are so special, and we call these two numbers the principal curvature. Okay. Now, when we talk about curvature, right now, usually we need a number, right? We're talking about number. So those are the two numbers. When we talk about normal curvature, it depends on direction, but essentially, there's only two numbers, key numbers there, and that's a K1, K2. So those are two numbers we call the curvature, principal curvature. Right. It's nothing to do with a surface patch here, but the question is how do you find it easily, right? That's a problem. Yeah. Right. To find the K1, K2, if we are able to find the basis, then also normal basis, such that the W1 equals K1, K1 W2 equals K32, then you can get a principal curvature. But sometimes it's much difficult to get principal curvature than the determinant. Okay, maybe it's easier to find the K1, K2, and usually, okay, what I'm trying to say that it is easier to find K1, K2, and K1 plus K2 than K1 and the K2. But if you can find the product, then you can determine K1, K2. The reason is lambda minus K1, lambda minus K2, when you multiply them out, you will get the sum here, right? So if you know the sum and the product, then you can use a quadratic formula to find the K1, K2. Okay, so just one more step. So all we need to do, it's sufficient in order to find the K1, K2, it's sufficient to find the sum of K1 and K2 and the product of K1 and K2, right? Yeah. To determine K1, K2, it is sufficient to determine K1, K2, the product of K1, K2, and K1 plus K2, okay? So first of all, let's introduce the notation. Here's the definition. K equals K1, K2 is called the Gauss curvature. Right? H, half of that, average value of this two. This is called the mean curvature. That's the mean value of the principal curvature. Why we call the Gauss curvature as a product? Because Gauss discovered that K1K, the product, is uniquely determined by the partial derivative of the coefficients of the first fundamental form. Okay. But let's find the formula first for K1, K2, and then I'm going to maybe talk about the Gauss contributions. Right? Okay. So, all right. So nature basis, we call it nature basis. So nature basis, right? It's given by that, right? So this is going to be A sigma U, B sigma V. And we use a nature basis because given a surface patch, you don't have a very special basis, just the nature basis you're given sigma, right? So because TSP is spanned by, you just use this basis. Then you determine the matrix. Okay. So it's NV equals C sigma U D sigma V. So that means with respect to this nature basis, you get this matrix. Either you try to find find using matrix, right? And this matrix, and changing basis, you will get similar matrices. So the trace, so the determinant of WP is just AD minus BC. So if we are able to find A plus D, if we are able to determine AB, AD, BC, then you are done, all right? So using the Gauss map, right? You differentiate and you write on the coefficients A, B, C, D, then you get a matrix. So this is giving the Gauss curvature, that'll be twice of a mean curvature. So in order to find the Gauss curvature using surface patch, you have to determine this matrix. How can I do it? Okay. Okay. Well, from here it's identity, right? So we can I'm going to make it easier. So negative use, this is a vector, okay? But we write it in this way. So it's going to be sigma U, sigma V, let's say AB, AB, CD, okay? Expressing it. Then I'm going to multiply sigma U, sigma V, the dot product. So here you get a matrix. Now this is a really matrix. Right, and this side is E dot E is E. Sigma U dot sigma U is E. Sigma U dot sigma V is F. sigma v dot sigma u is f, sigma v dot sigma v is g. Now, what is this on the left hand side? Left hand side is nothing but LMMN. So our matrix A, B, C, D is completely determined by EF, F, G is the inverse of L, M, M, N. So the first part, this is from second fundamental, first fundamental, this is from second fundamental from the coefficients. You can multiply this out. As a matrix, the inverse matrix can be written in the form like this: G, negative, negative, and the E. Okay. Now it's not the inverse matrix, right? Then you do the product. Okay. So yeah, different geometry requires linear algebra. So if you're using linear algebra, let's do the computation very quickly. So EG minus F squared, let's compute GL and FM. And GM FN and negative FL minus EM, and this FM plus EM. So this is a ABCD. Okay. The determinant is a little bit complicated than the trace. Okay. The trace is easy to compute, right? So the mean curvature is half of A plus D, right? So it's going to be 1/2 of, yeah, EG minus F squared. I can add them together, GL, FM. I have twice of M. So GL plus minus, right, twice of FM. And plus EN. I just need to consider those two terms. All right. Yeah. If it's harder to memorize the formula, you just memorize this one. This is much easier because the matrix is determined by this. Now, the Gauss curvature is product of those two. Okay, so Gauss curvature at the very beginning, it's difficult, it's complicated, the product. So it will be GL minus FM, and then minus FM plus EN, minus GM minus FN, and times negative L plus EN. And you do the computation, right? And it turns out to be, yeah, let's compute the computation, okay? It turns out to be EG minus F squared and LN minus M squared. Okay. You can verify this. So this two will be canceled out. Yeah, we can see that, right? EGLM, EGL, yeah. All right, so Gauss curvature. We also, in the last class, I remember the Gauss curvature. Nope. Yeah, this is the. So those are two formulas. So if you know the mean curvature, the normal curvature, right, and you know the coefficients of the second fundamental form, then yeah, you see that you can use the coefficients of first fundamental form and second fundamental form. You can compare the K and H. So if you really want to find place of curvature, then use this identity by using this identity minus, I think, 2h lambda plus k. This will be lambda minus k1, lambda minus k2, so you can find the k1, k2. Yeah, we will do some computation examples later. So now, Gauss curvature and the mean curvature can be completely determined by the coefficients. Although the definition is pretty abstract, those are using the principle of curvature. Okay, this should be independent choice of a particular surface patch. But yeah, with respect to this nature basis, I get a matrix for the Venn-Gott method, and that matrix has the eigenvalues, but we don't compute the eigenvalue directly. We just compute the determinant and the trace of the matrix, and we can express it in terms of LM and the EFG. Right. Gauss's contribution actually is the main contribution here. Why it's called Gauss curvature is Gauss can express. Okay. So here's my remark, which is due to Gauss, and actually K can be expressed in terms of E, F, G, and their partial derivatives. Okay. And the formula is very complicated. So this is another genius guy now, right? In the human history. But geometry, let me talk about geometry. The modern geometry, this is modern geometry, okay? Modern geometry was originated from Germany. Okay. Yeah, surprise. Then spread to the France, then United States, then some area in the world. Okay, that's in after World War II. Okay, some mathematician geometry, special geometry, and including Albert Einstein, okay, coming to the United States. Okay. So Germany actually made a great contribution, has made great contributions in modern science, mathematics, any other area, philosophy, for example. Yeah, it's amazing. Right. Okay. There's another way to take a look at. Okay. All right. So let's take a look at an example. My favorite example is is the surface of revolution. So we did a many, let me check. So we did a surface revolution. The surface revolution, at least in one direction, it's curved evenly, right? When you rotate the curve in the space. But other direction, you can, this is curved, not even. It depends on the curve you're given, right? Let's take a look at, surface of revolution. Okay, surface revolution. Okay, first of all, in the XZ plane, we have a curve, right? So this curve, I'm going to call it gamma. Gamma u equals f of u 0 g of u. And we also assume that the length is v1. Okay. So that means f prime u squared plus g prime u squared equals 1. Make it easy. Okay. Then we rotate around the YZ axis, right? So I'm very curious about the curvature of this surface. This surface, in the horizontal direction, it's curved evenly. But in the vertical direction, it's curved based on, depending on the gamma. Okay. So it would be very interesting to know those two directions, right? E1 and E2. How or the principal curvature, maybe in these two directions. Let's see. All right, so sigma yeah. So we already did a computation for the first fundamental form, and I think I also have formulas for the second fundamental form. Okay. Yeah, we otherwise we have to redo the computation. Now, yeah, let's go back to somewhere. Yeah, we already have a. Okay. So sigma uv is going to be f of u cosine v, f of u sine v, and g of u. Okay. And the first fundamental form, I don't use a du dv here. Okay. So for v lambda sigma u mu sigma v, the first fundamental form, right, is going to be E lambda square 2EF lambda mu and G mu square, right? So the second fundamental form is L lambda square 2M lambda mu and N mu square. Okay. Since we did the computation before, so I'm not going to repeat it. So I just have a list. Okay, E is going to be, okay, E is going to be 1, F is going to be 0, so G is going to be F squared. Now, F is 0 means the direction of V and the direction of U, they are perpendicular. Okay. The geometric meaning of this, okay, the geometric meaning of this is sigma U dot sigma V is 0. Okay, they are perpendicular. Okay. Okay. But that is probably true. Look at the picture, right? The tangent vector to the curve and the tangent vector to the circle. This is a circle, right? So look, they are perpendicular. Okay, that's a sigma V. That's a sigma U. Okay, then L is going to be F prime, F double 1 prime, G double prime minus F double prime and G prime. Okay, and the one in the middle is also 0. Delete this. Okay. Well, it's harder to tell what is the meaning of m equal to 0. Okay, because this is going to be sigma uv dot n, right? Negative sigma u dot nv, and negative sigma v dot u dot nu. That's going to be 0. Right. All right. So let's compute the Gauss curvature and the mean curvature. the Gauss curvature is Lm m squared divided by Eg minus f squared, right? Eg minus f squared, Eg minus f squared, just f squared. Okay, Lm right? Ln, yeah, and m squared, right? Now this one we have to modify. We cancel f at least, right? Okay. We have to use a property. We have to use a property f prime squared plus g prime squared equals 1. Okay, so I'm going to differentiate. Right? Okay, that's what I need. So because here's f prime, g double prime, g prime, right? And minus f double prime, g prime squared. So how about this? Right? This is going to be f prime negative f prime f double prime, right? Okay. Then you will get, I take f double prime out, I get f prime squared and g prime squared. Again, this is going to be 1. So end up with a very simple expression. Only depends on f, the y. Only depends on f. All right. So that is very interesting. Okay. So we know that here's the following. Okay. Properties. Okay. So I'm going to define fk t u in the following by the following formula. Okay. One is if k is a positive, okay, and this just a u if k is 0. And if k is negative, hyperbolic sign. All right. So you can show that okay, you can verify this identity. Okay. So that what does that mean? That means if I use this f, let fu to be fku, then I plug into the above formula, the Gauss curvature is going to be just negative k. Or maybe I use little k here, okay? Otherwise, it's a capital K. All right. No, just positive k. Right? So it is a constant. The Gauss curvature is constant k. So I can construct the surface. So let's see what kind of surface looks like a Gauss curvature is constant k. Right? When k equals 1, I choose sine u fk equals sine u. So when u is a 0, it's a 0, right? When u is a pi over 2, Right. When f equals this, then g must be another one, right? So gu, otherwise it's not working. I have to make sure gu is going to be the derivative of this, will be cosine ku. Okay, so just a derivative. Derivative of this divided by k. Yeah, I want to make sure this is going to be the derivative both of them can be zero, right? So we can also define gk similarly. Yeah, and I want to make sure gu equals gku. Okay, so gku is going to be change sign to the cosine. Okay, change sign to the cosine. Okay. Then f prime squared plus g prime squared is going to be 1. Yeah, so we want to make sure this curve we choose I go too fast. The screen's it's going to be 1. Okay. So if I let k to be 1, that's easy, just sine and cosine either both, right? Otherwise, you be very careful, have to define the gk. Okay, so I think the gk u should be equal to cosine square ku divided by k if k is positive, and 1 if k is going to be 0, and hyperbolic cosine if k is negative. Okay, so anyway, so this satisfies the given information. Then you compute it. K is going to be the Gauss curvature is going to be k. Now let's take a look at the case when k equals 1. When k equals 1, okay, the curve depends on value of u, right? So in this case, gamma u equals sine u, 0, cosine u, okay? So when you u is a 0, that is point here. When you use a pi over 2, this is a point here. When you use a pi, this goes here. So u is between 0 and the pi. And what do you get? The surface of a revolution is a sphere. Okay, so the Gauss curvature, yeah, in this case, Gauss curvature is 1. Okay, now when k equals -1, I'm more interested in this case. Okay, then gamma u is going to be hyperbolic sine u, 0, hyperbolic cosine u. Okay, now in this case, the value of u, yeah. So this is the x-axis, so this is the z-axis. This is y-axis, right? All right, so the curve led you to go, yeah, how do you describe this curve? So we let u to be positive. Let's try this side. Okay. I want to make sure this is a derivative. Let's see. When I differentiate, no, we are not able to guarantee. Yeah, my computer, this GK is wrong, okay? So I have to be careful to choose. It's not just like this. Okay, this is wrong, okay? I have to make sure the choice. Yeah, I have to, let me go back to here. This is this is wrong, okay? Otherwise, I just want to make sure the derivative. Okay, let's go back. I want to make sure fk prime u plus gk prime u should be equal to square equal to 1, because f prime k equal u is going to be hyperbolic sine square k in k is negative, right? Yeah, and plus g prime k u square equals 1. Okay. So, okay. Then from here you solve for it's not it's not easy to solve it. So I think my construction is only in the positive case it works, but we have to spend a little more time to think on how to get g as a part of the function, because I have trouble to construct this. All right, and then from here you you get I think 1 plus okay, then you integrate it, then you get gk. Okay, so so be careful to construct the other quantity. Okay. To construct the other quantity, then g of gku equal be the integral of this. When u is small, this is the difference. Okay, yeah. Okay. So anyway, so the function you have to construct must satisfy this property, and then you get a curve, and you can construct surface something similar to like a home, okay? Yeah, and when you rotate, and the curvature will be negative, okay, -1. Okay, so we so that just look at 2 special examples. Now I'm going to also try to calculate the mean curvature. Okay, the mean curvature is defined by, right, Lg minus 2mf plus ne, right, and Eg minus f squared. So I will get Eg is here's f squared. little f squared. And LG, okay, f prime g double, that's L, right? Minus f prime g prime, this is L, and the g is f squared. Okay, since mf is all 0, so it's 0, plus n is f g prime, and e is just 1. Okay. So the mean curvature is a little bit more complicated. Yeah, we cannot simplify it further. Yeah, let me try this, okay? So let's see, f prime g double prime f squared minus f prime f and the f square and here's g prime, right? Plus f g prime f squared. I don't see any no. Look at the sphere case. Okay, look at the case. Case when f is going to be sine u, g is going to be cosine u, right? Okay, then you plug them into the formula 2h. F is sine square u. Okay, then f prime cosine u, and g prime is negative cosine u, okay? G double prime. And f square sine square u, okay, minus g prime is positive, okay, sine u. F double prime is negative sine u. And f square is sine u square. Plus f is a sine u. And g prime is again negative sine u. And let's simplify it. You will cosine square sine square is going to be 1. So negative sine square u minus sine square u. And here sine square u. So it's negative 2. Okay, so h is going to be negative 1. All right. So it's interesting, right? So K, so what are the principal curvatures? Principal curvatures, right, is going to be given by this minus 2h lambda plus K. So it's h plus 2 lambda plus 1, which is lambda plus 1 squared. So you have a 2 principal curvature, which are all negative 1. Okay. All right, and yeah, it's not surprised it's a sphere, right? So the principal curvature are all equal to negative 1. The reason it's negative, not positive one, is because of due to the choice of the normal vector. Okay, if you choose a normal vector going all sides, then the surface is curved away from, evenly curved away from the normal vector. So that's why the curvature is going to be negative. Now it's negative 1 everywhere. That means in all the directions, the surface curved evenly. Okay, the surface curved evenly. Okay. So why we have to introduce the Gauss curvature, mean curvature? Because they're numbers. You don't need to always mention the direction. Okay, if you don't care about the direction, yeah. So it's sometimes it's better than the no. It's easier to handle. It's better than the normal curvature in some. You have to keep telling people that the normal curvature in some direction, normal curvature in some direction. Okay. Okay. So for surface, it's not surprise. You need two curvatures to describe a surface in three-dimensional space. So do some comparison. Here's a plane, right? Curve in the plane. Okay, you just need at R2. Curve in the plane, you need a sine curvature, Ks. Sine curvature, right? So you can describe the curve in two-dimensional plane. Sine curvature. So it tells you how curved the curve at that particular point. Then for the surface, right, it's a two-dimensional object in three-dimensional space. At every point, you need a Gauss curvature and the mean curvature. You need two curvatures. The geometry of each curvature is different. They're different from each other. Okay, and that describe the local geometry of the surface in three-dimensional space. Now, then you say, well, curve I have two quantities, curvature and torsion, because you put a curve in three-dimensional space. That's why you have the curve has more freedom to curve. Okay, so that's why you need more quantities to describe the curvature of the curve. But how about I put a curve in the five-dimensional space, seven-dimensional space? Yes, in five-dimensional space, you need six curvatures. No, you need four curvatures. In a seven-dimensional space, you need six curvatures to describe the curve. Okay. So the surface, if we put a surface in three-dimensional space, you need two numbers to describe the curvature. And here we use you can use a K1, K2. You can use a Gauss curvature, mean curvature. They're equal, right? That can be determined from each other. But if I put the surface in the four-dimensional space, think about it. You maybe need four curvatures, not just two. Okay. What the Gauss discovered that is the Gauss curvature is completely determined by the intrinsic geometry of the surface, which means it's independent how do you put the surface into the space, in three-dimensional space, okay, without the stretching and the compressing. Okay, for example, okay, trying to get some sense of the Gauss curvature. Okay, so piece of paper, flat. Okay, this is a piece of paper, flat, right? You can put in three-dimensional space. Okay, you can put in three-dimensional space. So x-axis, y-axis, z-axis. This is our z-y plane. Okay, so clearly Gauss curvature is 0. The mean curvature is 0 because the principal curvature are all equal to 0. Okay, then you bend it. Okay, you make it a cylinder. I just bend the surface. I did not compress, stretch, deform it. Kind of just bend, right? Yeah. So this procedure keeps the distance between 2 points. The distance between those 2 points still in the space on the surface the same to the end. If the end cannot see the ambient space, it's on the surface. Then from point A to point B, keep walking. You don't see any difference. Okay. And then suppose this two-dimensional plane is gradually curved to make a cylinder. And probably cannot tell the difference. Okay, so this procedure, if we calculate, we find out that the Gauss curvature remains unchanged. Okay, the mean curvature in this case, if the radius is going to be r, okay, the radius is going to be r, then I believe that's 1/12. Okay. Okay. So that's why we want to study two curvatures. One is Gauss curvature. This actually can determine what's inside two-dimensional space, two-dimensional surface. Yeah, I can get, if I get enough data, I can determine. But I cannot determine, if you don't look at the ambient space, I cannot determine the mean curvature, because mean curvature, it tells you how, it's how it is curved relatively to, in the ambient space. Okay, think about why I have to talk about this. Our universe is a three-dimensional space. Imagine, I compared to here, so two-dimensional. We cannot see the four-dimensional space. I'm not talking about time. Okay, and then so we can measure distance between 2 points, just like an ant. Ant can measure the distance between A and B, and now on the cylinder, we are three-dimensional object. We can see it, but to the end, I only can measure the distance from A to B, and he finds no difference. Okay, but using distance between 2 points, what the ant can determine, right? Ant still think it's a flat surface. Okay, no. But we put this flat surface into a three-dimensional space. It's already curved, looks like, right? So n can only tell the Gauss curvature, which is 0. Okay, so our human being in three-dimensional space can only tell how three-dimensional space is curved. Our space is curved. Okay, that's proved by Einstein's theory. Okay. And but we cannot tell, based on the information we collect, what's inside our universe. We cannot tell other curvatures. Okay, for three-dimensional space, we can talk about Gauss curvature similarly. So, but there are many curvatures to describe our three-dimensional space. Okay, if we know our three-dimensional space is put in a four-dimensional space, five-dimensional space, then we should have other curvatures. But those other curvatures we never able to figure it out, because we cannot leave our universe. Okay, is that clear? Yeah, we cannot leave our universe. That's it. Okay. So I hope this example, yeah, we should understand it more. But Gauss proved that Gauss curvature is completely determined by the first fundamental form. The first fundamental formula we use it to measure distance between two points on the surface without leaving the surface. Okay. All right, let's stop here, and we'll continue next time.